Come on, can you? Oh, right, that keyboard's unplugged because I only have 2 USB ports. Okay. So, just in case you don't know which session you're in, this is Return of the Clustering, Kubernetes for Drupal. Now, you might wonder if this presentation is already online, and the answer is yes, it is already online at github.io. So go to socketmunch.github.io/return-of-the-clustering, and you'll be able to find this presentation and all of the links that are in this presentation. So I'll give everyone a minute to actually write that down. It's a little bit faster than in person because you can actually use a keyboard because there's a keyboard in front of you right now. All right, that's 15 seconds by my clock. Let's take another peek. If everything's okay. Are we okay still? All right. Tricky running all of this, especially with one keyboard not working. Okay, so you might be wondering, who is this weird person in front of you? Why are they just as a Jedi? And do they really get that excited when they have a boarding pass for a business trip? The answer is yes. I am Tess Flynn, otherwise known as Socket Wench. That's wrench, not wrench. It's been a long day already. I'm a module maintainer, blogger, and educator, and a DevOps engineer at 10.7. 10.7 is a full-service Drupal web agency. We create and care for Drupal-powered websites. We're based out of Minneapolis, Minnesota, but we are a remote company. We can work with you where you are. We can come to you, or you can come to us. We provide a number of different services: site hosting and migration. We provide Drupal 9 upgrades, site audits, process consultancy, and a whole bunch of other things. Give us a hi at the wonderful humans at 10.7.com. Now, as you might guess by this ridiculous getup and the way that this entire presentation is structured, this is in fact part of a trilogy. Yes, this is in fact the third of a cycle of presentations I have been giving the last few years. The first one is Ride the Whale, Docker for Drupalists. The next one is Avoid Deep Herding, Deployments Beyond Git. And again, both of those are a link to the presentation. So, a couple of years ago, my boss came to me and said, you know, we already use Docker locally. Wouldn't it be great if we use Docker in production? And of course, you know, being a DevOps person and, you know, aiming to please and having a self-loathing nature, I go, sure, yeah, that'd be great. And then a tumbleweed passed between us. But, well, let's talk about Docker in production. So earlier, I was actually looking at how to put Docker into production. It couldn't have been that hard. You get a Docker host, you put Docker on the server, you put server in the production, you attach point a domain name at the server. What's so hard about it, right? So I decided to do a little research. And I didn't think it could be that hard. So I went and looked and, well, quickly found out that a lot of people were concerned about the security issues, that there are some concerns about the performance related to it, and others had less than constructive additions to the discourse. And I realized that this was not going to be so simple after all. So let's address these points. The first one is Docker security. Docker maps the users between the host operating system, that's the hardware the server is running on, and the container operating system, that's where the applications are running. And it maps the user between these two environments. And unfortunately, most containers that you can find on Docker Hub and elsewhere run as root, which means that all the containers have root access to your underlying servers, which is not good. Now, yes, there is some sandboxing involved and some permission scoping so that they can't do absolutely everything, but there have been and are security breakout mechanisms that you can use to actually compromise the underlying host operating system of a Docker host from inside of a container. So that's a bit of a problem. So to fix that, we're going to use only containers that we have vetted ourselves personally, that we've assured have no security compromises, that have a chain of trust when it comes to how they're built, and that they don't run as root. The next problem is, how do we pass configuration? We're used to passing configuration with Docker through environment variables. So in Docker compose.yaml, you're going to set a bunch of environment variables to say what the database password is, where the database is, API keys, and a whole bunch of other stuff. And that's fine locally. But in production, it comes at a bit of a problem. And the reason why is because programmers do not treat environment variables with the same security consciousness as they do files, nor does the operating system. The operating system tends to say, if you can get this shell, you can get all of the environment variables. Now, some Drupal hosting providers will still use environment variables to pass configuration, and I'm not going to name any names, but if you go to admin report status, scroll all the way down to PHP, click more info, you can find your database password. That scares the heck out of me. So let's not do that. Let's instead use a facility that's built into Docker called secrets or config maps in order to pass configuration around. Okay. So we have the containers not running as root, and we're using secrets instead of environment variables. So we should be fine, right? Now all we have to do is take all of our containers, put them on a server, and wait a minute. What if we want to do this with multiple Docker servers? How does that work? Single node Docker is really, really easy. You run all the containers on the same system. You only have to install Docker once and everything works as expected. The only problem is that it is very, very difficult to actually spread that out to multiple servers. Plus, if you need to scale the server up to add more resources, you're going to hit some certain technical limits. Some hosting providers will not be able to add more than 16 gigabytes of memory to a particular server, or so many CPUs to a particular server. And it's actually been estimated that in x86 architecture, if you add more than 16 cores to a system, in most applications, performance goes down, not up. What's really missing is we need a component of orchestration, something that coordinates all the different Docker hosts to act as one to deploy instances, distribute load, and deliver resources. Now, Docker has one of these built in. It's called Swarm Mode. It's Docker's own orchestrator, and it is built in and free to use. If you have Docker installed right now, you can use Swarm Mode right now without paying anything extra. So, sure, let's try Swarm Mode. It can't be that hard, right? So what happens is we enable Swarm Mode on a Docker host. That becomes a node inside of the swarm. Yes, I know. Drupal, nodes, networks, nodes, nodes. So just bear with me here. And we can add as many Docker hosts to our swarm as we want. Each one, and that makes up our swarm. And if we need to add more, we can add more, and it's not a problem. The problem with this, though, is that swarm mode isn't really a complete solution. It's actually only part of it. In order to actually get traffic into the cluster to the correct containers, we need a swarm-aware load balancer to direct the traffic to the correct node within our swarm. We also need to set up some kind of external persistent storage because Swarm doesn't care about persistent files. And if you have a web server that's on one swarm node, and the files are on another swarm node, you're going to have a bit of a problem. So we need a way to configure that externally, and that becomes a complexity. So really, Swarm is only one piece and not the whole cluster. Also, Swarm mode was just really kind of difficult to work with when it came to scaling it out as an organization. At one point, we did have a hosting choice of Docker Cloud, which was used to run Swarm mode as an enterprise scale, and it was really expensive to run. And then they discontinued it, probably because it was so expensive to run. So the only choice you've got left is to self-host and sort out the load balancer and storage. And some people will do this and have done this and continue to run swarms today. I have one client which actually still runs everything in Swarm. The problem, though, with Swarm mode is that it's really uncontrolled to me. It just doesn't feel like I have all the knobs that I want to turn. Containers are really the only manageable unit within Swarm. And every time you deploy a container, an internal load balancer also gets deployed. So if you tried to and because there's no way to configure that or control it, you're going to have a lot of problems making that application performant and resilient across multiple servers. So, I was really disappointed when I found all this out. I thought, man, I should just go back to traditional servers because this is just not going to happen. But then I found something, like a relic from another age. And when I found it, I knew things were going to be different. So let's talk about Kubernetes. I mean Kubernetes. Kubernetes is an open source container orchestrator. It's created by Google, but today it is maintained by the Cloud Native Compute Foundation. What really attracted me to Kubernetes is its expressive power. Pods are only one of many manageable units within Kubernetes. And this allows you to tailor Kubernetes to your application, not the other way around. And this is particularly important with Drupal because from an infrastructure perspective, we really treat Drupal kind of like a black box. We don't know what's in it. We just put core on the site, we put the modules on the site, and then there's some custom code, and that's it. We don't want to go deep into the core of Drupal to change it to work on Kubernetes. We'd rather make Kubernetes work with Drupal, and you can do that. So how does this work? Well, every Kubernetes cluster is made up of one or more worker nodes. So you get a worker node, and on that worker node, you're going to run pods, which are the instances of your application. You also need a dedicated server called a manager node. This manager node is the one that monitors the state of the cluster to make sure that everything's actually working and coordinating correctly. If one worker has a problem, the manager node can direct all that traffic elsewhere. And we can actually add as many worker nodes as we need to and take them away as we need to. In fact, there's actually auto-scaling rules which allow you to add and remove them based on load, which is really, really powerful. And this is our Kubernetes cluster. And we can actually connect this directly to the internet through several different ways. Now, persistent storage is still actually a bit of a difficulty, but we'll get into that. And this is just really how Kubernetes works physically. This is not really how you interact with it. How it interacts logically is that you're going to define something called a deployment. And the deployment describes your application. Your application is going to need to communicate to internal and external services. So we're going to define those application endpoints by defining a service. So in this case, we have a service which allows our application to be accessed from the internet. If we actually need to do persistent storage, we can ask Kubernetes for a volume claim. And the volume claim represents a request for that storage. And then the underlying hosting providers can allocate that for us. If we need to interconnect multiple applications together, we just reference the service object. We don't need to actually reference the underlying application or get the actual host names. Kubernetes does all of this for us. So there's a lot of ways to describe your workload, and this is really just part of the Kubernetes model. It's really, really complicated with lots of subtlety and lots of layers, but this is the layer that actually worked for what we need to do in the Drupal world. So this actually covers just what we need to know. So let's review. Deployments describe an application, not just what containers to use, but the number of copies of that application called replicas, health checks, and placement within the cluster. Then there are services. Services are consistent application endpoints. They can be internal, external, or load balanced. Finally, there are volume claims called persistent volume claims, PVCs, not a pipe. There are requests for persistent storage, how much, from where, and how shareable it is. Also, when we deploy all of this stuff out, it's actually really easy. Everything in Kubernetes is written as declarative YAML and then pushed to the manager node for deployment. If you've ever worked with Drupal 8 or Drupal 9, you've probably seen a config file. If you can read a config file, you're a DevOps engineer now. Congratulations. And that YAML can be patched, diffed, and replaced just like Git. It's really, really useful to actually work with this in this fashion. It's amazing what you can do. Just this morning, I actually upgraded a Solr server, and all I had to do was replace the description of what the Solr server was, and the cluster did the rest of the work for me. It was very hands-off. When I saw this, I never imagined there was this much DevOps in the entire galaxy. Although, you know, Poe gave me kind of a bit of a look for that reference. So, this is great and all, but where do we actually use this stuff? Yeah. So let's get into our speeder and let's go to KubeStation. So we can always self-host Kubernetes. We can do this internal on existing hardware or external via a third-party VPS service. And sometimes self-hosting is your only option if you have legal obligations like HIPAA. There's less lock-in because one Kubernetes is the same as the next Kubernetes is the same as the next Kubernetes. They're all Kubernetes. There's no reliance on special APIs. But the consequence of self-hosting is the same as it always is. It requires staff to manage the cluster, to set up storage, to install security updates, and so on. One common pitfall of self-hosting Kubernetes is to assume that it is a secure by default configuration, but it's not. It's actually an insecure by default when you install it, and you need additional expertise and time to make sure that all of those points are closed and locked down. Storage is still tricky because you can actually set this up in a number of different ways, and Kubernetes still doesn't do the storage itself, but rather interfaces with the storage system. So you could use a traditionally managed NFS. Kubernetes supports that out of the box, or a SAN, but you could also use Ceph, Rook, or Heketi, and each of these has native Kubernetes integrations. So when I set this up once over a weekend just to see what it was like, it was a lot of resource just to run one cluster. I tried standing up a cluster of 2 nodes and 1 manager node, and it was coming to $50 a month, and I'm a colossal cheapskate. And it was too much money for me. So I didn't want to pay for all of this and the manager node. So maybe there was an easier way? Well, turns out there is. Managed Kubernetes is very much like a VPS, but for Kubernetes workloads. And this field has exploded in the last couple years. There's a number of different hosting providers which allow you to just say, I want a Kubernetes cluster. They give you a Kubernetes cluster with the number of nodes that you specify, and then you can configure it and run whatever you want on it. And most of these hosting providers only ask you to pay for the worker nodes and not the manager node. Also, the storage configuration is already baked in, not to mention security configuration and updates. There's a number of different providers which provide Kubernetes hosting: Amazon, Azure, DigitalOcean, Google GKE, and a whole bunch of other ones. And really, I can't tell you which one is best for you. It's best for you to go out and experiment with each one of these. See which works best in your organization. Which one aligns with the services that you already use? Which one are you more comfortable using? At 10.7, at the end of this process, we ended up on DigitalOcean. And DigitalOcean is a worldwide Kubernetes provider. They have a really easy REST-based API. Seriously, you only need to use curl to actually talk to it. And the pricing is really, really clear, really clear. If you actually go and allocate a cluster, they will tell you the price per month up front. A lot of other hosting providers, your only option is to get a bill. All right. Now we know that all of this is defined as YAML in our cluster. Let's start talking about building our cluster. So first of all, we're going to build our cluster out of 3 worker nodes of the smallest nodes that DigitalOcean provides. Why the smallest? Because we're going to assume that if we need more resource, we can scale it up. And we'll know that as soon as we start putting workload on the cluster. Also, we're going to use 10.7's flight deck for the containers because we already control these containers because we're 10.7. I've written those containers. They are actually production ready. They're security verified, and they've been working in Kubernetes in production for over 2 years now. So if you want to take a look at those, there's actually a link there for how to get Flight Deck working on your system. So we're going to first start with a MySQL node, a MySQL container, and we're going to back that by a persistent volume claim disk in our cluster. Then we're going to have 3 Memcache instances. Why 3? Well, we have 1 Memcache instance per 1 worker node. That way, no matter where our containers are running, there's a Memcache instance which is local to it. Okay, and then we're going to have 3 web engines. Wait a minute. What the heck is a web engine? Well, a web engine in our terminology is Varnish and Apache/mod PHP. Here's one thing that's a little bit weird about Kubernetes. Unlike Docker, where one container is one process, in Kubernetes, one pod is 1 or more containers. So in fact, we actually have a web engine, which is 3 pods, and each pod is 2 containers, one that runs Varnish, one that runs Apache/mod PHP. Why not Nginx and PHP FPM? We were more comfortable with Apache PHP, and the thing is that with this architecture, there's not that many advantages to running PHP FPM because you can always scale out with this architecture. So we decided to make it easier on ourselves rather than harder. Then we're going to connect all of this to the internet so that we can actually get traffic into the cluster. So here's what that starts to look like. We have so the first thing of this YAML is that you'll notice that there's an API version right at the top. This is not your version of this file. It is not your version of your application. It's not even the version of Kubernetes that you're talking to. It's actually the version of the Kubernetes API that you're defining this object in. And that sounds really confusing and difficult. And trust me, I have to web search it every time for what version I'm supposed to use. So in this case, for a deployment, it's going to be API version app/v1. Kind is a deployment. So we're going to make a deployment. It's going to have the name of web under the metadata section. We're going to have 3 replicas, 3 instances of this application, and we're going to assign it a label, which is a key value pair called app=web. And we'll see where that's used later on. Then we're also going to specify which container we're going to use. We're going to use 10.7/flightdeck-web. There's actually another one down here hiding, 10.7/flightdeck-varnish. And then there's some ports that we're also going to be opening. We're going to open port 80 for Flight Deck Web and port 6081 for Flight Deck Varnish. Now you might be wondering, if we run multiples of these, aren't they going to have a port conflict? The answer is no, because these ports aren't externally available. They're actually virtual ports, and there's a whole bunch of weird networking involved. Just trust me, there's a port there, and it's port 80 and port 6081. Next, we need the service definition. API v1, just a different version because Kubernetes. Kind equals service. Metadata equals name equals web. Wait a minute. We named our deployment web and our service web. Does that conflict or is that special? It turns out it's neither. Because they're 2 different kinds, the names don't conflict, so that we don't need to worry about that, and the names aren't used to match the 2 together. Instead, I like naming my deployments and my services the same thing because they're so tightly related that it allows me to know that this service and this deployment are for each other. Then afterwards, we have the spec. Inside the spec, we have ports, port 80 for HTTP, port 6081 for Varnish, and then we see a selector. And this selector is the important part. So you'll notice the selector says app=web. Well, app=web is what we specified in the deployment. We go back, we'll see that right here, app=web. So Kubernetes has a number of different deployments with all the label that all have the label app equals web. And this service says, well, I'm going to represent deployments which represent app equals web. And that's where that linkage is. So the selector and that label are the key point. Finally, there's a type at the bottom, and we're going to load balance any traffic into all of these different web containers. So we're going to have it type load balancer. Okay, now we need to worry about the database login. Where does the database login go? Well, in order to put anything that's particularly secure inside of Kubernetes, we're going to create a secret. A secret is defined as its own object, and it is mounted into the deployment as a disk, as a series of files. So here's what a secret looks like. API version 1, kind equals secret, metadata name equals MySQL, and then below hand we have several different secrets within this definition. And each one of these has a file name and then a base64 encoded value. Why are they base64 encoded? It turns out the reason why is because YAML is persnickety, and making everything base64 encoded makes sure that YAML stays happy. That's why. Afterwards, they're actually encrypted inside of Kubernetes, inside of its storage. So it's not accessible until it gets mounted onto a container. You'll notice also each one of these is a file name. That's actually not really standard. I like doing that because it reminds me how these get externalized inside the container. So when this secret is mounted inside of a container, we'll see 3 files with the unencrypted, unbase64 encoded content of each. Okay, how do we use this secret? So we go back to our deployment, and we're going to change it a little bit. So you'll notice that now we actually have a definition that's going to be deployment, web, same as before, but now there's a new volumes section. And in this volume section, we're going to define a new volume called vol_secrets_db. That's a name that we just came up with, and it's only valid within this deployment. And it's going to be a volume that draws its data from a secret called MySQL, which is the secret we just created. Then we're going to mount that inside of the container, specifically inside of the web container. We're going to have a volume mounts section. This volume mount section specifies where those secrets are going to be mounted as files. So we're going to say we're going to mount the vol_secrets_db, which we defined above, and we're going to mount it at /secrets/MySQL. So when this container actually runs, we're going to find /secrets/MySQL and then DrupalDB-name.txt, DrupalDB-user.txt, and so on for us to access. And that's how secrets work. That's it. It's a little bit roundabout, but you can figure it out. Okay. Now all we have to do, because we have all of this worked out, we now figured out what persistent volumes look like. Now we just need to get a disk, and we're going to share it between all of the web replicas, and everything will be great, and that will be for our site's default files, right? 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 No, it's not that easy. So it turns out that a lot of persistent volume claims are actually going to be single writer only. So you can only allocate a disk as being able to be read and written to by a single container. And this is actually a big problem because it means that we can't use it for multiple web pods. So that kind of kills the entire purpose of our entire cluster, doesn't it? How are we going to work around this? Well, it turns out that when we started working with this, this was a very difficult problem. We tried NFS, that didn't work for us. We tried a number of different solutions, and what we ended up doing is we realized the best file system was no file system. So instead, all of our sites actually have Fly System or S3FS installed on them, and we back that by an S3 compatible object store. So everything is served out of S3. Why? The reason why is because, well, really, the reason why is because we've been spoiled. In Drupal, we're used to having an attached disk to every individual server, and we can use that for sites' default files. The problem is that the content that we typically upload to Drupal sites is considered static or non-complex data from a cloud architect's perspective. And why is this difficult? Why is this different? Well, it turns out that that data doesn't need what's called block storage, which is the kind of storage which we're used to having, an attached disk. So what we really need, and so what is complex data anyways? It turns out that complex data from a cloud architect's perspective is the files which make up a MySQL database. Yeah, I don't think that we're uploading that to sites' default files. At least we shouldn't be. So we don't need that. And S3 compatible object stores are multi-writer by default, and some of them have CDNs built into them as well, so that we actually don't need to worry about content delivery networks either. Now, when I say S3 compatible object store, that doesn't necessarily mean AWS S3. It can be DigitalOcean Spaces, it could be Minio, it could be your own Ceph cluster. There's a number of different ways that you can provide an S3 compatible object store. So it's not just AWS. So that takes care of the files. Now we need to worry about connecting some of these pieces together. It turns out that we don't want Kubernetes load balancing for MySQL, because MySQL and load balancing doesn't exactly get along. And Memcache, it turns out that the Memcache module can load balance itself internally. So why are we doing the extra work? Let's have Drupal do that instead. The problem is that we do need predictable host names for this integration to work. How we do this is we actually create a special kind of deployment called a stateful set. It's a special kind of deployment where the host name is assigned deterministically every time that we spin up a container. Now, a stateful set pretty much looks like a regular deployment. API version apps/v1 kind stateful set, name, in this case, it's memcache. We're going to have app equals memcache as a label. There's a new service name field here, so we can explicitly specify what the service is. There are 3 replicas, and then below that is our containers, memcached version 1.5, and we're going to open port 11.2.11. Okay, we also need a service for our stateful set. So services work also with stateful sets. Name memcache, and then we're going to open port 11.2.11. We're going to have our selector app equals memcache, and then to turn off Kubernetes load balancing, we're going to specify this line. This line, cluster IP equals none, tells Kubernetes, don't assign an IP address, don't assign a special host name, don't do anything. Just let the service exist. And the reason why is because we want to advertise to Kubernetes that this is an API that's available so that it can create the necessary DNS host names. But afterwards, don't do anything else. We're good. We've already told you what we want you to do. Now, we still have one big open question, which is we need HTTPS. And we don't want to have multiple certificates for every individual web engine instance that we have to update and maintain. That's too much work. Instead, we want to terminate SSL as soon as it comes into our cluster. And we can do that using an ingress. Now, an ingress is a Kubernetes-managed edge load balancer. It actually runs as a series of containers inside of Kubernetes, and it actually handles multiple domains. So you can map multiple domains to Kubernetes services and host multiple sites out of the same cluster. And yeah, it can terminate SSL. Here's what an ingress definition looks like. This is the part which describes to the cluster how to route traffic. So this is called an ingress definition. This is different than an ingress controller, which is actually handling the traffic, just to let you know. So API app/v1 kind equals ingress. We have a number of annotations here which control how network traffic should be routed to this particular service, including fixing rewrites, making sure that sessions are going to be sticky, that CORS is enabled, that proxy, that we have sufficient size for file uploads, and so on. And then afterwards, we're going to have a TLS section, which specifies how we're going to do SSL. For example.com, look in a secret called Ingress to actually get the certificate chain. Below that, we actually have all of our routing rules. So here's our routing rules. Host example.com on path/, we want to look for a service name called web and route it to 6081, which is the varnish port. And that's all you need to do to route traffic. So what about that Ingress TLS secret? This combines is the combined certificate chain, not only your certificate, but also the root certificates that go along with it. So your immediate certificate provider, and also your private key. You need to have the private key in order for that certificate to be validated and useful on the server. And this is defined as a secret. So API v1 kind is a secret, and it has two different keys, tls.cert and tls.key. And they both contain the base 64 encoded certificate chain and private key, respectively. But, Tess, there's a problem, isn't there? Like, what about Let's Encrypt? We don't really want to keep paying, this protection money for a bunch of prime numbers in order to actually have our site be secured. Let's Encrypt does this fine. It works great. How can we use Let's Encrypt? It turns out that there's a project already out there called Cert Manager. It's an open source certificate store and provisioner, and it works with Kubernetes out of the box. You can find it at cert-manager.io. What if we want to host multiple sites out of the same cluster? We might start getting naming collisions, and that's a bit of a problem. So the way that we solve this as 10.7 is that we actually have one site equals one namespace, and we name the namespace after the URL of the site. This way, all of the different deployment names, service names, stateful set names can all be consistent across every individual site, so that as soon as people know what those names are, they only need to check the namespace to work with a particular site. And it works out perfectly wonderfully. We don't need to worry about a lot of different names or going to hunt for them or reading a lot of YAML because we already know what the model is. So to me, this architecture is really just DevOps happiness. It's all right there for me. So now that we know what the cluster will look like, how do we actually get it into DigitalOcean? So let's get into our exo, and we're going to have the build chain of Yavin. So we know that everything is based on YAML in Kubernetes. And how do we deploy this YAML? It turns out it's one command. Kube control apply -f and then the path to your YAML file. And then repeat this for every YAML file that you need to deploy. If you are using namespaces like we are, you can use the -- namespace parameter or -n parameter in order to specify where those objects are going to end up in the cluster. The namespace also has to exist first, and there's a link there that describes how that actually works. Now, it would be easy to take all of these files, all of these separate individual definitions that we have to create, combine them all into one giant YAML file, and then we only have to do apply -f once. And when we need to update it, we just do apply -f again with the updated file. We don't need to edit it. We don't need to patch it. We can just reapply it, and Kubernetes sorts itself out. The problem is that that doesn't really fix what we have here. We really need to remove human beings from the process because human beings can be stressed out, could be exhausted. They could have several weeks of unrest in their nation and their city, and it would be very difficult to sleep for several weeks. But what we really have is repeatable clusters. We really need to be able to make our clusters repeatable because clients tend to only differ in things like sizes, logins, and some features like Redis versus Memcache. Wouldn't it be great if we could just define those differences and not have to rewrite the same YAML all over again? Well, yeah, that'd be great. And our solution was to use Ansible variables and the Kubernetes module to template that YAML dynamically. So how it works is that we have our DevOps engineer. They're going to write a bunch of group variables for a particular site, and that gets committed to a Git repo. GitLab CI picks up that commit, takes the playbook and hands it over to Ansible. Ansible is then going to start standing up the cluster by talking to the DigitalOcean API, and then we'll start deploying out all these YAML definitions through kube control. So it does all of this work for us automatically. How do we authenticate this? First, we have to create a personal access token within DigitalOcean. Then we're going to pass that to the DigitalOcean API as an HTTP header. Now that's a bit complicated, so we're going to have a bit of automation to handle that too, and I'll get into that in a moment. What about creating the cluster itself? We can create it manually, and sometimes we still do create it manually, but we also have the 10.7.DigitalOcean role on Ansible Galaxy, which can spin up an entire cluster for you. It handles scaling, node pools, and a whole bunch of other stuff. So here's an Ansible playbook for what that looks like. Here's our personal access token, and then we have a definition here called DigitalOcean clusters. We're going to create a cluster called my.k8s cluster in the SF2 region. It's going to have 2 node pools, both of the smallest size available. The web pool will have 3 servers in it. The DB pool will have 1 server in it. And then we're just going to hand all of that over to the role, and then it executes and builds the cluster for us. How does kube control get authorized? Now, when you do this manually, DigitalOcean is going to give you a file called kubeconfig, and that kubeconfig contains an authentication token inside of it, which talks to the cluster. The problem is this file gets regularly re-rolled by DigitalOcean, and it can become invalid. So instead, we have another Ansible role, 10.7.DigitalOcean kubeconfig, which dynamically reprovisions that kubeconfig file so that we can actually authenticate with kube control. And that's all it does. To use it, here's another complete Ansible playbook, hosts all vars, DigitalOcean kubeconfig, the cluster that we need to talk to, and where to put the kubeconfig file. Finally, we call the role 10.7.DigitalOcean kubeconfig. All right, what about writing the Kubernetes YAML itself? We have another role for you. The 10.7.flight.cluster role is going to provision your entire site for you. It creates secrets, deployments, cron jobs, services, Solar. It deploys GitLab runners. It deploys an Ingress controller. It does all of this stuff, and you can find out all about it on the documentation on GitLab. So yes, you can find the documentation on GitLab. It's at github.com/10.7/ansible-role-flight-cluster. All right, so now we have our new fancy Kubernetes infrastructure. We can stand over those other for-profit Drupal hosting providers, and we can say, "You failed, Lord Hostedness, for I am a DevOps like my mentor before me." I should probably get a site onto the cluster now, shouldn't I? Yeah. Let's do that. All right, we're all clear, Kate. So let's deploy this thing and go home. So, well, I'm actually already home. You're probably home as well. That's cool. Usually, we're used to updating in place. That's the normal deploy strategy for shared hosting and VPSs. The servers don't move; the code moves. This usually is done via SFTP, Git deploy, and some CI systems. Please use a CI system. I don't care which one, just use one. The problem on Kubernetes is that we need to deploy to each replica of the web engine because each one is practically its own server. Or we have to use NFS to host code. This introduces a number of performance hits in our infrastructure and makes it slower. That's really... It's not how the K8s works. So the more I thought about it, the more I realized that the site code that we write, Drupal, the modules, any custom code, the theme, is the application. It should be the container. So what happens in our infrastructure is that a developer is going to make a commit to a Git repository. that that commit is picked up by GitLab CI. GitLab CI looks inside of the repository and finds a Docker file. The Docker file contains all the infrastructure and all the information necessary to build the Drupal site, compile the styles, run Composer, everything. Once that's done, that image gets saved as a Docker image, which contains the entire site code. And that gets uploaded to an image registry for access later. Then GitLab CI is going to talk to kubeconfig and say, you need to update the site. And kube control is going to actually pull the new version of that container from the registry and deploy it out to the cluster. And that's it. That's how our infrastructure works. You can find an example Docker file on how to build Drupal inside of a container at github.com/10.7/flightdeck-Drupal. This creates directories, builds Drupal, runs Composer, and it also does some initial configuration as well, which you can pass via either files or environment variables. Yeah, there you go. It writes settings.php for you. So what about that private registry? Well, a private registry stores built site-specific Docker images. Now, this is like Docker Hub, but it's your own Docker Hub, and no one else can get to it. And the reason why we want to do that is because we don't want to upload our site images to Docker Hub, obviously, and have anybody run them. We want to keep them to ourselves. Now, Kubernetes needs an authentication token to communicate with a private registry. And of course, because it's Kubernetes, we store that token in secrets. You can find out how to get that token and how to stand up your own private registry on docs.docker.com. Okay, so now in order to use our new container, we're going to need to modify our deployment. So API version app/1 kind equals deployment, blah, 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 blah. But then it gets different. So down here, it's different. So image pull secrets, we have a name for my registry key, and my registry key is going to be a secret which contains the authentication key necessary to talk to the registry. We've also changed the image name. So now it's myregistry.tld. So this is the address of your registry, the port of your registry, and then the image that we want to get. And finally, the version of the image that we want to get. Now, this version isn't important right now, but it will be in 2 seconds. So this is all great, but how do we control the update? Once we deploy this out, we need to deploy a new one, right? And we don't want to have any downtime. So how do we handle that? What we want to do is we want to do a rolling update. And in a rolling update, it replaces running containers with a new image and does it sequentially to eliminate downtime, so that we don't need to worry about deleting all the images, having a 5 to 10 minute outage while we're updating the site, and then bring new instances all up all over again. Instead, we want to tell Kubernetes, why don't you update the first one? Once that's ready, do the second one. Once that's ready, do the next one, and so on. And Flight Deck Cluster does this for you too by default. So we need to modify our deployment definition, and we're going to add a new strategy section. We're going to say that we want to do a rolling update, and we're going to say we want to add one additional server each time we want to we do a deployment, and we want to only work with one server at a time, one container at a time, sorry. And then every time we update a new container, we want to wait a minimum of 5 seconds between each container updating. Now, there's a little bit of a gotcha here that's not really talked about in this. If we go back to our deployment definition, you'll notice there's a version number here, 107. Now, you can, if you deploy a new container and tag it with the same tag, 107, essentially overwriting that, you're going to have a problem. Kubernetes will not know that you need to do a rolling update, and it will do nothing. The problem is that even if the underlying container image changes, as long as the tag doesn't change, Kubernetes doesn't do a rolling update. So what we actually ended up doing is we don't use version numbers here. We actually use the commit SHA, because the commit SHA is always unique and always changes. So we use the commit SHA, and every time the deployment happens. So it's really, really easy. If you want to find out more about Kubernetes, you can go to kubernetesbyexample.com. It's an online book. It's a little outdated at this point, but there's still a lot of useful information in it. You can use the interactive tutorial on kubernetes.io if you want to actually do this right inside of your browser and start working with Kubernetes. You could also look at 10.7's own Hosting Drupal on Kubernetes class, which is on YouTube and GitHub, so that you can run a 4-hour hands-on example class by yourself. And that's it. There's a whole bunch of other resources online, but those are the ones I like. I just want to give a special thanks here for DrupalCon Global for having me here today, for 10.7 for sponsoring my time, for my wonderful patrons on patreon.com/socketwunch, which helped me do this and a whole bunch of other weird projects. And thank you. You can find this presentation on github.io. Now we see if people are still around. Oh, it looks like it's still running. Yay. I wasn't talking to myself for the last hour. And as predicted, I'm 4 minutes over. Okay, I'm not sure if there's any questions, but you can always find me on Twitter if you want to talk to me, or on the Drupal Slack. Sometimes I still check that. There's one question: how do you handle stateful storage like sites' default files? Okay, so again, we actually store that in an S3 compatible object store. We don't actually store it inside of our system, inside of a persistent disk, because most hosting providers, DigitalOcean included, only do one writer by default. So by using an S3 compatible object provider, it's multi-writer by default. That also handles PHP Twig as well. So a lot of those also, Fly System and S3FS are pretty smart, and they actually know where to put each one of those files. So we actually haven't had a problem with that. Don't quite understand when DB update and such fits in. Okay, that was actually a fun problem. The problem is that when we do a rolling update, there's no immediate callback to our CI, whether or not that the deploy has finished. So what we ended up doing is we actually buried into the configuration, and we found out that you can actually have a blocking call in kubectl in the newest versions of kubectl. So we block the call, wait for the deployment to complete with a timeout of 5 minutes. And the reason why we have that timeout is because the way that Kubernetes will fail typically is if you do a deploy and the container doesn't start up, and Kubernetes will keep trying to start it up again and again and again and again. So after 5 minutes, it just kind of gives up and says, yeah, something went wrong here. I don't know what happened. And then you have to investigate it. Once you actually have that deployed out, the next thing you have to do is get a running pod. So we actually call Kubernetes, the kubectl again, get a running pod within the namespace for a particular deployment, and then you can use kubectl exec to run drush to run updb. And it's kind of a weird hack, but it works. And we've been using it for 2.5 years now, so sure. Anything else? Why Ansible instead of Helm? Okay, that's another good point. When we started working this was 2.5 years ago, and it was Helm 2. Helm 2 requires an on-server privileged resource called Tiller. And the problem is that we didn't want to support Tiller because that actually has a number of security implications for our clusters. So we decided to go with the technology that we were comfortable with, and we already were comfortable with Ansible, so we used Ansible. We do have some plans to actually convert Flight Deck Cluster to Helm now that Helm 3 is around and we don't need to use Tiller. But there just hasn't been time yet, and I'm still working on it. I might be able to write a blog post on denonet.com for that eventually, but I haven't gotten to it. Oh, geez, the questions are coming so fast. Do you run updb when the first updated container is up or when the last replica is up? When the last replica is up, because you don't know where the next request is going to come in, so you wait for the whole deployment to finish. And that can take about 3 minutes, and that could be a little bit hairy depending on the kind of update it is. But it's the best, most consistent way that we found to make it work without doing some weird dynamic scaling stuff. Let's see here. How does your development pipeline of dev stage prod fit into this architecture? So we actually have 3 different namespaces for every site. We have the first namespace, which is the prod site, another namespace, which is the test site, and a third namespace, which is kind of a throwaway shared feature branch environment, because we don't have the necessary infrastructure yet to do per feature branch environments, although we could if we could figure out the database part. So we actually have each one of those, and every time we commit to, say, develop, it goes to the stage environment and gets deployed out. If we commit to preview, it goes to the preview environment and gets deployed out. We commit to master. We're changing that to main pretty soon, actually. It gets deployed out to live. Along the same lines of DB up, how do you handle Drupal cron tasks? So Kubernetes actually has cron built in. I didn't really cover it in this presentation, but the way cron works in Kubernetes is that it actually is a separate container. So we just have cron. Now Kubernetes spins up a new web container, and we tell it to run a command that is just drush cron, and we tell it where all the stuff is in the container, and that's it. It just works after that, and it's been working for years. It's great. Consequently, if you do things like recurring migrations or third-party integrations that require background tasks that need to access shell, you can still use the same thing. And because it's the web container, it has all the same code, so it's not a problem. Let's see here. Anything else? That's it. Okay. I think that was the last question. I think I hit the leave button. I can finally hang up my Jedi outfit.